Okay, today we begin vector kinematics, and kinematics is a um, term used in physics for motion. So it's motion describing vectors. If you want, you can watch this, The Amazing Free Kick. But you can use vectors to predict motion. You can use it to forces. Um, if it's straight, it is not necessarily a constant acceleration, which might make it more challenging. Because spinning balls do weird things. But the concept vectors help to quantify positions and movements. They provide tools for enhancing your spatial awareness in 2 and 3 dimensions. We're doing a lot with 3 dimensions. This topic provides you tools for analysis, measurement, and transformation of quantities, movements, and relationships. So, constant velocity. If you don't have constant velocity, you need calculus. If you have constant velocity, you can use some equations. And those equations are in your physics data booklet that I handed you. This is page, well, it's what they call page 5. It's probably the 8th or 9th page. I'm going to tell you what these mean. A lot of times we'll use different variables in physics. So V is velocity. U equals what's often in physics called V0 or initial velocity. I don't know why they use U. Sometimes I use V sub I, but this uses U. S stands for position. A is acceleration, T is time. This one, that's very bad. It should actually be labeled, actually, they should be delta S. This should be delta S. This one should also be delta S. So apparently S here stands for change in position. I don't like that at all. V stands for current velocity, or what we often call final velocity. And so this one is just the change in position is the final plus initial over 2 times time. Essentially average velocity times time. The final velocity squared is the initial velocity squared plus 2 times acceleration times change in position. These are all kind of developed through calculus. This one's really pretty easy to develop with calculus, and once you learn calculus, I'll show that. So change in position is initial velocity times time plus 1/2 acceleration times time squared. These are only, and I can't stress only enough, for constant acceleration. That means your acceleration is a number like 5 or negative 9.8. They are not for accelerations that have a formula like 5t. If you're going to do those, which you might have to, you have to do some calculus. It's not terribly hard calculus. That's kind of some of the easiest calculus. So those are our constant acceleration equations. Those are probably the only ones that you really need out of this physics booklet, but kind of those ones are pretty important. So we're going to use vectors, and what we're essentially going to do is break some of these equations into separate x and y equations, or do it with vectors that relate the acceleration to the acceleration as a vector. So here we have a ship traveling from port A, the origin, travels at velocity 3040. That means it's going 30 kilometers per hour this way. Your vector is like this. Well, no, not quite like that. That's not a good drawing. Like this, 30, 40. Your actual vector is the diagonal, but the components are very useful. How far will the ship be from port after 10 hours? I know velocity S equals U times T, or distance equals rate times time. 30, 40 times 10 is 10. So my position vector S is 300, 400. The question was how far. So I used Pythagorean theorem, right? The coordinates. Well, that honestly, that was easier. It's already done. Now I use the Pythagorean theorem. 300 squared plus 400 squared is 500 squared, or 500 kilometers from port. So let's do another one. A drone flying in a straight line starting at 212 with a constant speed in meters per second. After 10 seconds, its position is 4334. Find the velocity, vector, and its speed. So if you remember, S is change in position. So my change in position vector went 2, 2, and 1. So S again equals U. No, not U. I guess it's constant velocity, VT. So initial velocity is the velocity at all points, but or the old distance equals rate times time. Rate is a velocity, distance or S really stands for displacement. So it's kind of D would be absolute value of S. So change in position, but nonetheless, this is S. T is 10. So my velocity vector is 2 over 10 or 1/5. 2 over 10 or 1/5. If I want to show the it says find the speed. Speed is going to be the magnitude of velocity, which means essentially that direction vector on the angle. And we'll just do this, and I know that the decimals are 0.2. And I get speed equals 0.3 kilometers per hour. Okay, our next one. Position vector at time t for an object moving, for a moving object P relative to a fixed point O is given by OP. So 1ijk plus T times 2I minus K. Find the coordinates of the initial position of the object. So ijk is 1, 1, 1. I'm going to put this in I'm going to put this in like the matrix notation. Ijk is 1, 1, 1 plus T times 2, 0, -1. Find the coordinates of the initial position. I'm plugging in 0 for T. So 1, 1, 1. Find the coordinates when T equals 2. So 2 times 2 is 4 plus 1 is 5. So I'm doing the top line. 2 times 0 is 0 plus 1 is 1. 2 times -1 is -2 plus 1 is -1. The coordinates I should write in point form. Hence, find the distance traveled by the object in 2 seconds if the velocity is given in meters per second. So if velocity is in meters per second, it's going to be meters. The distance traveled is going to be the difference between the vectors. Oops, not equals. Difference, so I'm going to subtract. And then it asks for the distance. So this is a movement vector. Distance is going to be, use the Pythagorean theorem. So 16, 17, square root of 21. I suppose I should give that as a decimal. Because in applied math, we want decimals. 4.58. So to 3 sig figs, 4.58. And it does want this to be in meters. Oh, would help if I subtracted correctly. 1 minus 1 was not 1, it's 0. So that goes away. This becomes square root of 20, which is not 4.58, but 4.47 meters. The position vector at time t of a moving object, it is given by this. OP equals R, which is -t squared 1, 2t. Show the path of the object is not a straight line. Well, I could do things like plug in 1 at t equals 1, I get -1, 1, 2. At t equals 2, okay, I'm recording a video. I'm recording a video for class. It's okay. At t equals 2, I get -4, 1, 4. At t equals 3, I get -9, 1, 6. Clearly, this is not a straight line. I'm interested to see how they did it. Oh yeah, they just did a bunch of them. And when you subtract, they should all be the same if it's a line, and they're not. So comparing the ones. Essentially finding the slope between them, not all the same. And they could call this, if we wanted, we could call it A, B, C. So B minus A, here is how they're justifying it, equals -4 minus 1 is -5. 1 minus 1 is 0, is 2. C minus B is -9 minus -4 is also -5. 1 minus 1 is still 0, is 2. Wait, maybe my object is moving in a straight line. We do have the same points. -9 minus -4 is -5. Oh, -4 minus -1 isn't -5. It's like, this shouldn't be the straight line. -4 minus -1 is -3. Since these are not the same, there is no unique slope. Or what they did was they showed vector equation for a line, which essentially this is 0.1 minus 0.2, and there's a constant slope here, k 0.2 minus 0.3, and so that should work with the vectors. And if you can't get the same k doing these subtractions, it means it doesn't work. Colliding objects. An initial aircraft, an aircraft A has position vector at 900 hours given by r equals 023 kilometers relative to an airport. It is moving with velocity 345 kilometers per hour. A second aircraft is given at 900 hours at 455 and is moving with velocity -113. Show that the two aircrafts will collide at point P and write down the coordinates of P. So I need to start by writing their two equations. So their position is going to be given by initial position plus their velocity times time. All right, let's not call it S, we'll call it A. This is aircraft A. And B is given by this position plus there's times time. So essentially, I've just got two vector equations for lines. And they're going to intersect at some t, which will be a point P. So I'm going to set them equal to each other. So what I can do is I can just solve these one at a, take one line of this, the x line, and solve it. So I have 4t equals 4, giving me t equals 1. I need to double check that that's true for the other two lines, or this is not a true statement. So I'm plugging in 1 for t. 2 plus 4 times 1 is just 2 plus 4. That's 6 equals 6. And then I'll do the third line. That is true. So t equals 1. If I want my point, I'll plug in 1 for either one of these. Let's do the top one. T is 1, so I don't really need to multiply by anything, giving me 3, 6, 9. So that is my coordinates of point P. So the trick to showing it was writing the two vector equations for lines, solve one of the lines and show that it equals the same on line 2. So maybe I should have labeled this. Line 1, line 2, and line 3. One more example, and that'll be it for today. Two objects are moving with constant velocity in a straight line. Initial object A is at a point with coordinates 1, 3, 0, relative to a fixed origin, is moving with this velocity. Object B is initially at coordinates -1, 1, -2, relative to a fixed origin, moving with that velocity. Show that these objects do not collide. Yes. So my two equations are (130) plus (-342) t, and B is (-1, 2, (-2) plus 2, (-1, 3). And so I'm again going to just solve the first line and set them equal to each other. 1 minus 3t equals (-1 plus 2t. Let's solve this. by adding 3t to both sides and adding 1. And I get 2 equals 5t, t equals 2/5. So I'll check that on line 2. 3 plus 4 times 2/5 is supposed to equal 2 plus -1 times 2/5. And that side's 3/5. This side is 8/5 plus 15/5 is 8 plus 15 is 23. These are clearly not equal. So the two objects, when they are at the same x coordinate, are not at the same y coordinate, so they're not going to collide. They're going to pass by each other, but not collide. Find an equation in terms of t for the distance between the objects. Well, distance between the objects is, difference in x, difference in y, or in this case, I could write this equation for A. Might be easier to think of it in the physics notation. 1 minus 3t I hat plus 3 minus 4t j hat plus 2t and 0 plus 2t k hat. And B, -1 plus 2t I hat plus 2 minus t j hat plus -2 plus 3t k hat. The distance, I just subtract the things squared. 1 minus 3t minus -1 plus 2t. Three minus 4t minus 2 minus t. All under that square root. So I'm going to simplify this. 1 minus -1 is 2. My -3t, that's going to become minus 2t, is minus 5t. Plus 3 minus 2 is 1. -4t plus t is minus 3t. Plus 2t minus 3t is -t plus 2. So this is a formula for my distance. It might not be the simplest one, but it says find their closest approach. So I'm going to minimize. I think the easiest way to do this is to graph it. And I could expand that out and simplify it more. And there's a calculus technique for minimizing, but I think it's just easier to graph. So we're going to graph. I'm not sure I'm done, so I don't want to erase a bunch of stuff. But I'm going to enter that equation, and I am going to use x instead of t. And I get a graph that looks like that. I analyze graph to find the minimum, and I get 0.397, 1.64. So I'm interested in the x, so 0.397. So t is 0.397 is when they will be closest. Let's go back and check those answers. And then find the velocity of the object that B must have so that the two objects will collide after 3 seconds. Okay, so I can get rid of some of this. So when they came up with, they solved all 3 of them and came up with different ones. I think you could solve one and plug it in and show the same thing. Um, so again, they came up with, I believe that's the same thing they had. When they put them together, and they decided to simplify it down. They got a different answer than me. Um, so 2 minus 5t, 1 plus 5t, and 2 minus t. I'll have to look again here. They've got a 5 here. I pledge allegiance to the flag of the United. Okay, different value. 1 plus 5t. Oh, there's a typo. Okay, 0.137. So 0.137. So finding a new velocity. So we get a slightly different vector. We don't know A, B, C here, but we want them to collide at 3 seconds. So I'm going to take my line 1. And I'm going to plug in 3 for A. So this is -8. We have 1 plus 3A. A equals -7/3. I'll do the same thing with the B line. 3 plus 4 times 3 is 12. Minus 3B. So 15 minus 2 is 13. -13/3 is B. And then I'll do the same thing with the C line. And it ends up being 8/8 equals C. And it gives us the velocity vector. Did I have the wrong? Oh, this is a plus. It's that's plus 3B. I was looking at one of my other ones. What I did that and saw the negative, but I don't know the negative. So positive 13/3, and that becomes my velocity vector. So the key is just manipulating these things in vectors and doing a lot of line-by-line equations. You can leave them in vector form if you want as you're doing these line by line, but sometimes I think it's easiest to just do them line by line. So that is 13.12.1.